Okay, so today I'd like to introduce you our new quantum theory, called it MRSF-TDDFT, which has been wonderful for our applications, and hopefully it'll be useful to you too. Okay, so whenever talk about the new quantum theory, we need to think about the electron correlations. Basically, we as a quantum chemist, we all know that we have a dynamic correlations and non-dynamic correlations. The best way to treat the non-dynamic is a CASSCF, and Klaus Rudenberg is the one of the main creator of this theory. And Mike Schmidt next to it always told me that CASSCF is a one and the only theory, nothing else. Well, that's not really true. But you can easily know that there are a lot more theories out there. We tried to do the non-adiabatic dynamic simulations, something like more than 10 years ago. And then we looked at all the quantum theories we have at that time, but I realized that something is missing. So that's why I had to develop something new. So let me tell you why I thought about that. First of all, DFT certainly includes dynamic correlations, but we know that it fails to calculate our radicals. Therefore, people developed a theory like a broken symmetry DFT. On the other hand, the TDDFT is a wonderful theory for excited states, but no doubles. That causes some troubles in many cases. And there's yet another very nice theory. To me, it was a wonderful theory at that time. Spin flip TDDFT, that actually includes doubles, but there is a problem, spin contamination. Sometimes it's very severe. You cannot identify its spin states. And of course, so there's CASSCF, certainly. And certainly this is the best method for non-dynamic correlations, but we know that it misses dynamic correlations. I will come to these points, showing you some examples why the consequences of this. So you might think that the multi-state, multi-reference perturbation would be something that has to do, but you know that it's too expensive for an AMD simulations. So we need something in the method that it needs to be with the practicality of DFT, but also we have to have some good accuracy of higher level theories. And we had to start somewhere. So we looked at the spin flip TDDFT because that includes doubles, even though this is linear response theory. So if we can somehow resolve the spin contamination problems, then maybe this theory can works very well. Well, it turned out we're not the first one to think about it. There are wonderful people already talk about this. So basically what they do is that, so let me first tell you why there's a spin contamination problem is. Spin flip TDDFT starts with the high spin triplet reference here that generates all these configurations with except that the red ones here. Because you cannot generate by single excitation, you have to do double excitations, which is too expensive. But the people trying to introduce higher excitations to generate these reds to eliminate the spin contamination. Well, we have a very much different idea because we thought that, well, these the red ones can be generated by another reference, which is M sub S minus 1, beta beta, by single excitation, which is very simple. And also it almost mirror image between the two. And you don't have to recalculate this, your system to get this because it's already there. So by combining these two references, you can generate all these necessary configurations so that you can eliminate the spin contaminations. Well, things is not that simple. As soon as you start using two references, then your density, your combined density becomes a non-idempotent, which is incompatible with the linear response theory. So it was a really difficult time to think about to overcome this. And we come up on kind of idea, like we call the spinor-like transformation. Somehow, idea is very simple. We could, by doing this transformation, we could combine these two references into a single hypothetical references. As soon as you have a single hypothetical references, your density becomes idempotent, and the rest is straightforward. So we were able to develop the energy, also soon derive its gradients. So basically the scheme looks like this. You start with RHF M sub s plus and -1 references, and you apply spin up and spin down single excitations that will generate M sub s -202 configurations. We use the 0 and we take the externally contract them, meaning that we impose spin adaptation to get singlets and triplets. By doing this, we eliminate spin contamination almost nearly. And then there is also remaining 2n minus 1 you can use to generate quintets. Okay, so from now on, let me tell you some performance of these theories in terms of the conical intersections. We know that the conical intersection has to meet the 1 point, and this is that's why it's a conical intersection. And so even though you locate the conical section, you really have to check that whether this is a cone shape. And MRSF-TDDFT correctly reproduced this topology, but you know that TDDFT has a long linear intersections, so meaning that too much interactions between ground and the first excited states, which is a big trouble for this. If you do the NAMD dynamics, it means that it goes to the ground, so it's too quick. But in our theory, we can show easily that we do have a proper topology of conical sections. Now, what about the conical section between excited states? Now, conical section 2-1, I think butadiene seems to be the really popular molecule in this conference. We try that to here. So there are two states that already people talk about here. The red is the Zibiter ionic states. That means that it requires dynamic correlations. And the blue is the multi-configurational dark states, which means that we need a non-dynamic correlations. So, so if you use high-level theory, you do have here the conical section between the two. However, if you use a CASA-CF, which does not have the dynamic correlation, your bright states too much, like more than 2 electron volts here, simply don't have any proper crossing here. And on the other hand, the TDDFT, which is dashed line here, it looks like that the red is below the blue. That looks okay at the front condom region, but in the conical section regions, this dashed line is supposed to go down, but it's not. It's because that the TDDFT does not have doubles. But on the other hand, our theory has doubles, so that properly this region is stabilized, so that we recover conical sections. We were very surprised and excited about this, the performance, because our theory not only described the any type of conical section well, consistent with the very high level of theories. This is a really key the points when you do a proper NAMD dynamic simulations. Okay, after that, we've been trying to expand trying to check in many other cases. Here, Toby helped us a lot, so that now we have a relativistic version of MRSF, so that you can calculate spin-orbit coupling. It looks like it's very accurate, and also we were able to combine the MRSF with the NAMD code, so we can perform that. Also, we checked this our theory for the X-ray absorption spectroscopy, because these days people are really trying X-ray absorption spectroscopy a lot. So there are lots of people is trying to simulate them, and it looks like they're very accurate, almost half electron volt accuracies. This is a really amazing accuracy because in the typically TDDFT up by more than 10 electron volts. So now you can easily simulate the TR X-ray absorption spectroscopy like this. Also, we developed the non-adiabatic coupling, correct calculations, and it's very accurate. Here you see that the black curve is from the full CI, all the colored solid lines from our theory, but it's not exactly matching, but it's almost representing correct the shape. I also like to mention that the theory can calculate radicals too, because we can we can generate all these configurations. So unlike the TDDFT, which cannot calculate ground states, our theory can calculate ground states. Therefore, we can also study this. Recently, also we are able to combine the EKT, extended coupon theory, with Dyson orbitals, so that we can calculate ionization potential electron affinity. So for the remaining time, I will just briefly show a couple of examples we did. This is thymine excited dynamic simulations. CASSCF saying that as 2 trapping, but our theory says as 1 trapping. This thymine is has the longest excited lifetime among the nuclear base, and people trying to understand the reason. But there is a lot of controversy like this. So we checked the surfaces, and we do have a conical section between 2, 1 here, so that our trajectory simply goes to the S2 to S1 quickly. But on the other hand, CASSCF, which is the solid line here, again, too much overestimates the bright states, so that it misses the conical sections. So there's no chance of going to the ground S1 states. That's why CASSCF is reporting the S2 trappings. Okay, we also okay, maybe I need to skip a couple of slides, and because this is Young Teller, so I need to say something about Young Teller. We also tried the Young Teller here, TMM, a very simple system, and the triplet is ground, and the 2 singlets are degenerate like this, and we tried it. This is the blue line, blue curve represents the triplet, so that at the high symmetry D3H, this is the global minimum. But the 2 singlet has a conical section right here, and that correctly presented. We actually also calculate XMS cos-PT2. Those values are underscored here. Our values are the upper number here. So if you look at all these numbers, the 2 numbers are quite consistent. So it looks like that our theory also can describe these kind of Young Teller distortions. So what are the features of our theory? Right now, we have formulated the RHF base, but we will soon have UHF versions, and also trying to improve other functionalities. So the conclusion is our theory is, I think, it's a good platform for balancing dynamic and non-dynamic relations. Therefore, we could properly describe civitaronic and multi-configurational electronic states. And also it eliminates spin contamination of simple TDDFT, so you don't have to worry about those. And also it looks like that quantitatively consistent with high-level theories. Also, you can calculate the ground states, open shell singlets, so that you can study bond breaking and the radicals. But this theory is still n to the 4th formally, practically n to the 3rd, just like DFT. So it's cheaper than any other high-level theories. Okay, this is the theory is right now in games right now, so you can download it. Please try it out.
Games.
Okay, and yeah, and so the input examples you can find here, so you can try. And also, I'd like to thank here Toby here. Toby pictures is right here. Thanks for everybody. And thanks very much for your attention.